And let me know if you have any questions while we wait for everybody else to show up. We got about 1 minute left. It looks like about 6 of you guys are in there. Feel free to ask me any questions if you have any. I just remembered I'd forgotten to do a certain type of problem for you, and I remembered it after I'd already prepared and had my notes in place to start the first example. So I had to figure out a way to put a new page in front of it and then put a new first example in. So I'm now working on that, and looks like we're about ready to go. So that should be good enough. So no questions. All right, well, I'm going to go ahead and get started. Last time we started working in capacitance. In fact, I'm looking at the notes right now, and it looks like the last thing we did was I used Gauss's law to compute the electric field above and below a infinitely large charged plate. I then argued that if you put one positively charged plate next to a negatively charged plate, that the electric field between the two plates will actually add. And therefore, instead of having sigma over 2 epsilon naught as the electric field, you end up getting sigma over epsilon naught as the electric field between them. And you get 0 electric field outside on either side. Then I used V equals a negative integral of E dot dl to compute the actual voltage difference between the two plates. And then I used the definition of capacitance being charge divided by voltage to calculate the actual capacitance of a parallel plate capacitor. And of course, we found it was C equals epsilon 0 A over D. So that was like the last thing we did. Now what I want to do is go back and show you how to work a little bit with capacitors. So I'm going to start off just by giving you the basic formulas for capacitance. And I'm going to give them to you while I actually show you this example. In principle, actually, let me see. Yeah, I can do this. So I've got one extra page. So I'm gonna go ahead and share my screen and show you the fundamental formulas for capacitance that you need to know. I'll tell you the capacitance formula. You can sort of think of it like the power formula that you know from electricity and magnetism. Specifically, we use P equals IV, but then we have this wonderful little equation, V equals IR, called Ohm's law. So if you don't know the current and the voltage, you can replace the voltage with IR, and then you get P equals I squared R. Or if you don't know the current, but you do know the voltage, you replace the current with V over R, so you'd end up getting V squared over R. All of those are acceptable versions of power. And we're going to do something similar to that when we talk about the energy stored in a capacitor. So first off, capacitance for a parallel plate capacitor. We derived that last time, and that was a fundamental paradigm I was telling you. In other words, one of the fundamental things that I think you should be able to do upon completing this course, and it's essentially like a litmus test of whether I think you should pass or not, is can you use Coulomb's law or Gauss's law? Hopefully Gauss's law, because it'll be easier, to one, calculate the electric field, let's say between two parts of a capacitor. That could be a parallel plate capacitor. That could be an actual coaxial wire that has a capacitance. It could also be two parallel wires, like the example in your book, they have a capacitance, or it could be two spheres, like the example I'm going to work in a few minutes. But the main thing is there's a lot of ways you can make capacitors, and you use Gauss's law or Coulomb's law to calculate the electric field between the positively charged part and the negatively charged part. Then step two, you use the delta V equals negative integral at E dot dl to calculate the voltage difference between the two parts. And then you use the definition of capacitance, C equals Q over V, for the third step, which is calculating the capacitance. So what we learned was that the parallel plate capacitor has a capacitance given by epsilon 0 A over D, and that's assuming you have air or a vacuum between it. Okay. If you don't have air or vacuum, you have some other, and in fact, to be honest with you, air technically is supposed to have a dielectric constant of 1.00, I think it's 1.0006. So technically you should have a kappa or a K in front of that epsilon 0, even for air, but unless you're interested in like the third or fourth decimal place, it really doesn't matter. If we have another dielectric in it, and again, dielectric is just a fancy word for insulator, then the capacitance becomes either K times epsilon 0 A over D, where this K is the dielectric constant. So whatever it's made of, whatever it's made of, you can look up the dielectric constant for that material, and that's what you multiply it by. But sometimes we choose instead to write it as just epsilon A over D, and then this is known as the permittivity of the dielectric. Okay, so that's the parallel plate capacitor. We also know that in general, C is Q over V, and that suggests, of course, that C is equal to coulombs per volt, and that's actually defined to be the farad, which you abbreviate with just a capital F. And more often we use a micro or a milli or a pico or a nanofarad than we do actual farads. But of course, you can also say C equals Q over V means V is equal to Q over C. And it also means that Q is equal to C times V. So there's the three forms of the definition of capacitance. I'll also tell you that when you have a capacitor charged up, then there's a certain amount of energy the capacitor has, and the formula for that, we call it a potential energy, so it's a U. And the one I'm most familiar with, or the one I remember easiest, is 1/2 CV squared, because that one reminds me of, for instance, the kinetic energy, but it also reminds me of the potential energy of a spring, where the spring will be 1/2 kx squared. And that's going to become relevant because later you'll have this, which looks just like, at least mathematically, looks just like the potential energy of a spring. And then you'll have another formula that looks just like the kinetic energy, which also could be looking like the potential energy of a spring. But in that case, it's an inductor. So you automatically know exactly how it's going to behave, because basically you have energies just like potential energy and kinetic energy for a spring. So now I can also say, like I did before when I was talking about power equals current times voltage, you could use Ohm's law to replace the V or to replace the I. Well, you can use the definition of capacitance to replace various things. So for instance, we could go ahead and replace the C with Q over V, and then you'd get 1/2 And then, of course, the C would become Q over V. So that's 1/2 Q times V, because one of the V's in the bottom would cancel out. Now, you could also, instead of replacing the C, you could replace the V with Q over C, and then you'd get 1/2 C times Q squared over C squared, which would be Q squared over 2C. So those are the three formulas that you use for the energy stored in the capacitor. And really, that turns out to be the energy stored in the electric field. And I'm going to use that a little later. Now, we also have to, and your book does a derivation here, or you can look up any of the videos where I talk about capacitance or introduction to capacitance in my YouTube channel. You'll see me do the derivation of the formulas for series and parallel capacitors. But basically, you don't have to memorize a new formula. It's literally the exact same formulas as you use for resistance, but they're in the opposite order. So for instance, 1 over C equivalent for a series circuit is 1 over C1 plus 1 over C2 plus ... So you'll remember that formula looks just like the resistance formula for resistors in parallel, where you'd have 1 over R equivalent parallel equals 1 over R1 plus 1 over R2 plus ... Similarly, for resistances in series, you'd have R equivalent series is equal to R1 plus R2 plus ... Well, guess what? When we go to C equivalent and parallel, then the formula becomes C equivalent parallel is equal to C1 plus C2 plus ... So those are some formulas we're going to use over and over again. It comes in handy to use them. I want to solve this problem right here, so I'm going to go ahead and steal it for a second. I'm going to actually copy it and pull it over to here. I'm going to say copy, and now I'm going to put it right here and say paste. And of course, for some reason, it keeps bringing my URL with it. So, oh, well, I'll just deal with it. So what we'd like to do with this case is we want to find the equivalent capacitance. So find the C equivalent for this capacitor assembly. Capacitor assembly. B, then, or let's not start with that. Let's just say find the voltage across and charge on each capacitor. So our goal is to use these formulas that I just introduced you to do all these problems. And in doing so, you will actually learn a little bit about how capacitors behave and therefore how, nature works. So first off, I want to tell you that let's do solution. It's going to be in red. So first off, I want to tell you that the battery basically has a positive side and a negative side. Of course, we knew that already. The long side is supposed to represent the positive side. And for all intents and purposes, you can sort of picture a battery as if it's just a cup full of charges. And you can imagine the charges actually pouring out of the positive end of the battery, even though generally speaking, the vast majority of the charges that are moving around in a circuit are charges that were free to move within the wire. And in fact, of course, you guys know that they're actually electrons, not positive particles. But the main thing is it doesn't matter too much. It behaves the same whether you're talking about conventional current or real actual negative charges. So this left side of this battery, the positive side, acts just like a big heap of positive charges. So all the positive charges want to run around away from that and then establish all the voltages as best they can across capacitors. And then those are going to scare the positive charges on the right hand sides of the capacitors, or the top in the case of the 3 microfarad capacitor. They're going to scare the positive charges away from it and force those charges to run to the next capacitor, and so on and so forth. So what we're going to do is we're going to take the 2 capacitors or more that I can actually apply one of these formulas to. So for instance, you look, you've got a 4 microfarad and a 5 microfarad capacitor. Notice how the fact that I've got the symbol drawn shows you it's a capacitor. So you know the unit has to be a farad. So I don't have to write anything other than the micro. But the 4 and the 5 microfarad capacitors are actually in series. And of course, we know the formula for capacitors in series is in fact the 1/1. So what we can say is 1/4 plus 1/5. Actually, let me do this a little differently. I'll say 1/C4 5. In other words, the equivalent capacitance for the 4 and 5 microfarad capacitor is 1/4 plus 1/5. Notice how I don't care about the micros and all that stuff. I can still work it out just fine. Of course, the least common denominator for 4 and 5 is 20. The way I do it just quickly in my head is I check and see if the smaller number, the 4, can actually go in the larger number, the 5. It can't. So then I try multiples of the 5. So 1 times 5 has already been tried. I try 2 times 5, that's 10. 4 doesn't go into that. 3 is 15. 4 doesn't go into that. But 4, of course, 4 times 5 is 20, and clearly 4 goes into that. So what we're going to do is we're going to multiply the 1/4 by 5/5, and we're going to multiply the 1/5 by 4/4. So I'm going to get basically 5 plus 4/20, which equals 9/20. So C45 is actually 20 divided by 9, which you can say, and that's 20 divided by 9 microfarads. Now, 20 divided by 9 can also be written as 9 goes into 20 3 times, because it's 3 times 9 is, or excuse me, 2 times, because 2 times 9 is 18. I've got 2 left over. So it's going to be 2.222. And that's carrying 1 extra sig fig. You can notice, for instance, I got 3 sig figs on everything. So when I did the other part, I should have came out basically with 9.00 over 20.0. And then that's 3 sig figs divided by 3 sig figs. So you should just get 3 sig figs there. But I'm going to call it 2.22 microfarads. Okay. So that means this circuit is actually equivalent to, now I'm going to change the orientation a little bit just so it's easier to write. Here's our 3.00 micro, and then that breaks up into the 2.222 micro, and opposite that is the 10.00 micro. And then this goes back to the battery, and this goes back to the battery. So that's the equivalent circuit so far. Now I've got the 10 ohm and the 2.222, or excuse me, the 10 micro and the 2.222 micro in parallel. And that's actually really easy to solve. So I can make the equivalent of this be basically, here comes the wire from the battery. Here's the 3.00 microfarad capacitor. It's going to be in series with a 12.222 microfarad capacitor. And I don't need the farad there because I actually got a symbol by it. Whoa. So 222 microfarad, which I just write micro. And now this goes back to the battery. So now I can do 1/3. Actually, let me rewrite that. I'm going to say this is the total C equivalent that we were looking for. So 1/C equivalent is equal to 1/3.00 plus 1/12.222. So I can just add these. I'm just going to do it brute force on my calculator. I'm going to say parenthesis 1 divided by 3, close parenthesis. We know that's 0.33333 plus parenthesis 1 divided by 12.222, close parentheses. That gives me 0.415153. So 41553, way more sig figs than necessary. We're supposed to have 3 sig figs, so these are extra. Now I'm going to say that C equivalent is, of course, 1/that. So I'm just going to raise that to the -1 power. And that gives me 2.4088. Microfarads. Of course, I don't have a drawing next to this one, so I actually have to put the farad on there. So this turns out to be the equivalent circuit. Basically, we have a 12-volt battery, 12.0 volts, and that is in series with a 2.4088 microfarad capacitor, like so. So that's the equivalent circuit. Anybody have any questions on the parts we did there? So that was part A. Now we can start looking for things. So for instance, as far as the battery is concerned, it doesn't know that there's really a 3 microfarad capacitor in series with a parallel bank that has a 4 and a 5 in parallel with a 10. It doesn't know any of that. In fact, all it can sense is that there's a 2.4088 microfarad capacitor on the other side. And according to the definition of capacitance, we know that the voltage ultimately is going to become 12 volts. And then the Q can be solved or found by multiplying the capacitance times the voltage. So again, on this final circuit where you see a 12-volt battery and a 2.4088 microfarad capacitor, the positive side of the battery is going to act like something that's scaring all the positive charges away. All those positive charges are going to run to the left side of the 2.408 8 microfarad capacitor. Now, because of that, they're going to stack up on this left-hand side, and every time one comes on there, that's going to scare away some of the positive charges in the right plate. So the positive charges that were on the right side of the capacitor, they're driving back in and sort of in some sense going back into the negative side of the battery. And that continues up until the voltage across the capacitor is the same as the voltage of the battery. And in some sense, current flowed. It didn't really flow because you can sort of imagine that essentially no positive charges jump that gap, but the equivalent of positive charges jump that gap. So there is something equivalent to current going around it. It's just not strictly speaking, one charge ever went from the left plate to the right plate. All right. But because of that scenario that I told you about, what you now know is that the Q for the 2.4088 microfarad capacitor is actually Q total, which means the total charge that leaves the battery. You can sort of think of this as like a current, because really, if you looked at a current for 1 second and the current was, let's say, 100 amps, then basically the current of 100 amps flowing for 1 second is equivalent to saying, well, 100 coulombs went by. So that's sort of one way you can think about it. If that helps you physically understand, then by all means use it. But it's basically going to be the capacitance, which is 2.4088 microfarad capacitance times 12.0 volts. And that gives me 28.91. It actually is 9050. So I'll write 9050 like that. And that's just carrying a bunch more extra sig figs. And that's actually microcoulombs. Now, if there's no capacitors in series with the battery, then no single capacitor is necessarily going to get that charge. But in this case, we actually have a 3 microfarad capacitor in series with the battery. So what's going to happen is 28.9050 microcoulombs is going to leave the left side of the battery and stack up on the bottom edge of that 3 microfarad capacitor. And then that's going to scare away an equal amount of positive charges from the top plate. And then that negative plate is going to become the exact same charge, but negative. So the negative plate will have negative 28.9050 microcoulombs. And then those microcoulombs, the 28.91 microcoulombs, is going to go to this junction, and some fraction of them are going to go to the 4 ohm, 5 ohm, or excuse me, 4 micro and 5 micro leg, and then some other fraction is going to go to the 10 microfarad leg. Now, you should know, of course, these are in parallel. So the total voltage across the 4 and the 5 microfarad capacitor is the same as the total voltage across the 10. So that should tell you from C equals Q over V that clearly the 10 microfarad is going to get the lion's share of the 28.9050 microcoulombs. We're going to do the calculation to make sure, but we'll see. So now I have the equivalent capacitance. I also have Q3. Now Q3, notice I actually used integers for the actual capacitances. So that's something nice I did so that you'd have a different number for each capacitance and we could label it. So what I just argued for you is that Q total is the same thing as Q3, and that's equal to 28.9050 microcoulombs, like that. So we now have the charge on the 3 microfarad capacitor. And you can also use V equals Q over C to compute the voltage drop across the 3 microfarad capacitor once it gets all that charge. Well, it's going to be 28.9050 microcoulombs divided by 3.00 microfarads. And you can see the micros cancel out, and I'm just basically dividing 28.905 by 3, and that gives me 9.635. $9.63500 volts. And that's the voltage across the 3 farad capacitor. So I'm going to say this is equal to V3. I'll circle it off or box it off. So now we know the actual voltage across the 3 microfarad capacitor, and we know the charge through it. And that actually helps us. Let me show you. So if I were to imagine taking the voltmeter, let's say a multimeter or something like that, let's say this is our multimeter. I'm going to draw it right here. And what you can do is, for starters, set it to read, let's say DC volts, which, you know, from the ones we've been using in class, they have a dash, 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 and then a solid line above it. So I've got it set to that. I'm not necessarily going to worry about getting the wires on the right side. I'm just going to call this the COM, and I'm going to put it on the right side because it's convenient. And then I'm going to call this the V omega, and I'm going to put it on the left side again because it's convenient. So if I were to imagine taking a wire and sticking it right here, and then I imagine taking the red wire and sticking it right here, what it would read is 12.0 volts. And I didn't do so good with that part. But evidently I didn't like anything, so I can just draw it all over again. And this is going to be connected to that. That's going to be connected to this. And this little red thing is going to be connected right there. And this is there. Okay. So now that's what I've got. Now, when I draw bubbles on these diagrams from now on, you'll understand that what I'm doing is just taking that red line and putting it in various places. So in fact, right here would be 12.0 volts. Oops. And now, since the voltage drop is 9 point, what did I get? 9 point, what were they? Oh, okay. 9.635. I'm going to subtract that from 12. And that's going to give me 2.365. So 9.365, or excuse me, 9.635 less than 12 is 2.365. So this will be 2.36500 volts, and that's what our little bubble will show. But if you look closely, you realize the only thing separating that little piece of wire at the top of that capacitor from the piece of wire at the left side of the 4-ohm capacitor is just a wire. Wires are conductors, and in some sense you can think of them as equal potential. So I can also say that the voltage right here is also 2.36500, and the same thing is true about the left side of the 10-ohm or 10 microfarad capacitor. It's going to have a voltage of 2.365. If you were to draw a bubble from there, you'd say that's 0 volts, because clearly they're at the same potential. Because remember, I was leaving the black line connected there all the time. So if I put the black line and the red line on the same spot, you should get a voltage difference of 0. Now I'm going to use that same argument I had before, that basically only a wire separates the right-hand side of the battery from the right-hand side of the 10-ohm resistor. And only a wire separates the 5-ohm or 5 microfarad capacitor. I know I said resistor a second ago, but 10 microfarad capacitor is what I meant. And the same thing's true about the right-hand side of the 5 microfarad capacitor. Right here reads 0 as well. So you can tell clearly the total voltage difference across the 4 and the 5 ohm resistor is 2.365, but we already know what the voltage across the 10 ohm resistor is. So I'm going to continue with my solution and say that V10 is equal to 2.36500 volts. So that's another answer. And now that also allows me to figure out that Q10 is equal to, if you look back here, you can see Q is equal to C times V. So we're going to say 10.00 microfarads. You know, that really looks bad and small. So I'm going to make it better. Times 2.36500 volts. And that gives us Q10 is equal to, obviously, 23.64. So 23.6500. Again, we're only entitled to probably 3 sig figs, so I'll underline all those. And this comes out, notice the micro was in there, so the micro stays and it becomes a microcoulomb. Okay, so now we know how much charge went to the 10 microfarad capacitor and the total charge that came into that junction. Notice right here, that's a junction. So at the blue junction, what was it, 28.9050, 28.9050 microcoulombs entered from the left, and 23.6500 microcoulombs left the junction through the lower wire. Okay, that means, so the upper wire gets 28.9, 0.905, dang it, 50 minus 23.6500 equals 5.255. That's 25501 microcoulombs. Okay, so we now know that 5.255 microcoulombs is going to balance itself on the left-hand plate of the 4 microfarad capacitor. And that's going to scare away the positive charges on the right-hand plate. And therefore, that plate's going to become equally negative. And that's going to force the right-hand plate of the left-hand plate of the 5 microfarad capacitor to have 5.25501 microcoulombs as well. And then that's going to force the right plate to run off an equal amount of positive charges so that it becomes negatively charged by the same amount. So now we can say that Q4 is equal to Q5, which equals 5.25501 microcoulombs. And again, those last three figures are not significant. So now I've got the charges for the 4 microfarad and for the 5 microfarad. I've also got the 10 and the 3. So I've done all the charges. Now all I got to do is the voltage for each of them. And we know that voltage, let's say V4, is equal to Q4 over C4, which equals 5.25501 microcoulombs divided by 4.00 microfarads. In this case, you see that clearly the micros cancel out and you just get plain volts. So dividing this 5.255 by 4, I get 1.3138. 1.3138 volts, and the 3 and 8 are extra sig figs. So now I have the voltage across the 4 microfarad capacitor, and the voltage across the 5 microfarad capacitor, V5, is Q5 over C5. And I don't like how my Q5 looked. So again, I'm just going to take the 5.255. Oops, did I write C4 down there? I really did, didn't I? I'm going to write C5. Okay, so I'm basically just taking the 5.255 and dividing it by 5. So you should get a little bit bigger than 1. And in fact, I get 1.05100 volts. So that's the voltage across the 5 microfarad capacitor. Now, if everything we did is right, then the total voltage across the 4 and the 5 should be the same as the voltage across the 10. So we should check that just to make sure we're right. So if I take that 1.0511 and add to it the 1.3137, so I'll say plus 1.3138 is what I rounded it to. That gives me, here you go. So my check is V4 plus V5 is equal to 1.3138. And remember, we're only supposed to have 3 sig figs, which is 2 decimal places on this number, plus 1.05100. And it's also 2 decimal places on this number. And when I add those two, I get 2.36, and that's 480 volts. What we see was V10 equaled 2.36500, and those weren't significant. But notice our first non-significant digit is in the 3rd decimal place of V10 and the V4 plus V5. That means if you actually rounded the 2.36480 to 3 decimal places, it would be 2.365. And if you rounded this one to 3 decimal places, it'd be 2.365. So even beyond the sig figs, we got agreement on the voltage. So that gives us some confidence that what we did was right. Anybody have any questions on that? Okay. That's it. That's the way, or that's the brute force way you go about solving a circuit with just capacitors in it. You can sort of, let me recap. You sort of can take any two or more capacitors that are currently in series or parallel, and you can go ahead and use the appropriate formula to find the equivalent. Then again, you can look after you've done that, like how I did on this diagram right here. I had already replaced the 4 and the 5 with something. Now I'm looking for two or more capacitors that are in either series or parallel so that I can combine them. I look at this and I see only the 2.222 and the 10 are in series or parallel. And in that case, they're in parallel. So I know they just add, and therefore I got 12.222. But of course, that's what's replacing the 2 in parallel. So the 3 is still there. Now I've got 2 in series, and that's the only 2 I can do anything with, and it's the last 2. So then I had to use the appropriate formula for them being in series, and got basically, as I told you before, when you have this type of formula, 1 over C equals 1 over C1 plus 1 over C2 plus dot dot dot. The equivalent capacitance, in this case capacitance, is smaller than the smallest one. Well, the smallest one was 3 microfarads, and in fact we ended up finding 2.4088 microfarads, so that is smaller than the smallest one. Now once I have that, that's the equivalent of all of those 4 capacitors, and that's all that really the battery senses. So all the battery knows is, hey, I've got a net capacitance of 2.4088 microfarads. So the amount of charge I'm going to send out is basically Q is equal to C times V. So the Q10, or excuse me, the Q3 that we were able to find is basically because the total charge that the battery lets out because of that 2.4088 is exactly the charge that the 3 microfarad capacitor gets. So all I have to do really with that 2.4088 is multiply that by 12 volts, and that gave me 28.9050 microcoulombs, which is this guy. Okay. Now, again, because the 3 microfarad capacitors in series with it, that's going to take the whole charge, because there's really nowhere else for the charge to go. If it was in parallel, you'd say part of it would go to one leg and part of it go to another leg, or however many legs there were. But it's really has no choice. Every bit of it's got to go on that 3 microfarad capacitor. So the Q3 is the same as Q total, is 28.9050. So that's why we got that for the Q3. And then, of course, V is just Q over C. So I can just take Q3 and divide it by C3. And that gave me 9.6500 volts is the voltage across the 3 microfarad capacitor. Now, that's not the whole 12 volts, which is good, because we wouldn't expect all the voltage to change in that first capacitor and there'd be no voltage difference across the rest of them. So it had to leave a little bit. And in fact, what it left was 12 minus 9.63500. So that's what I did. I said 12 minus 9.635 would be the voltage on the top side of the 3 microfarad capacitor. And that, of course, is the same as the voltage on the left of the 4 microfarad and on the left of the 10 microfarad. Hence, I wrote it there. You can see the 2.36500 is the actual voltage that I got for all of those spots. Now, because the 10 microfarad capacitor was all by itself and only a wire separated the negative plate of the battery from the right plate of the 10 microfarad capacitor, then the right plate was at 0 volts. So that meant the voltage across the 10 microfarad capacitor was exactly 2.36500 volts. So I know V10 was 2.36500, and then Q is just C times V. So all I got to do is take the capacitance, which is 10 microfarads, and multiply it by the voltage that it has, which is 2.3650. That's not very good looking. I tried to make the decimal a little more obvious, and I don't think I did a very good job. But anyways, let me fix this a little bit. Do this one too. So now I'm going to make this decimal clear. And I'm going to do something else with this one. There you go. Okay, so you got 23.6500. And notice that's consistent with what I told you. The 10 microfarad capacitor is going to need to take the lion's share of the charge so that it can have the same voltage that the little 4 and the 5 have. And in fact, it took 23.65 out of 28.91. So it really did take all of it. Then I used basically Kirchhoff's junction rule to figure out what charge went to Q4 and Q5. And that was just a matter of taking 28.9050 and subtracting from it the amount that went to the 10 microfarad capacitor, which is 23.65. And that gave me 5.25501 microcoulombs. And basically the way capacitors work is if they're in series, each of the capacitors will have exactly the same charge. So Q4 and Q5 are both 5.255 microfarads, or excuse me, microcoulombs. Now all we're left with is finding the voltage across the 4 and the voltage across the 5, and that's what we did. Any questions on that? All right, I wanted to do something else real quick so you'd have the result. So let's draw a line here, and I am going to use the formula. U is equal to 1/2 CV squared. Now I'm going to apply this to a parallel plate capacitor. Oops. And here's the weird thing. This is one of those times in nature that you look out, in that if you write the formula for the energy stored for a parallel plate capacitor in terms of the electric field, you ultimately get an answer that happens to be the fundamental general answer, even though you did it for the special case of a capacitor. And that's what happens here. So let me show you. We have 1/2, and then the capacitance of a parallel plate capacitor is epsilon 0 A over D. And then the voltage, of course, is the electric field times the D. So I'm going to say E squared D squared, because the V had to be squared. Does everybody follow that? Anybody have any questions? My chat window's not showing, so let me check that real quick, just in case anybody typed anything. It does not appear anyone's typed anything, so that's okay. All right, so I'll go on. So just remember, V equals E times D. That only applies with a uniform electric field. And that's exactly what exists between the plates of a parallel plate capacitor, at least as long as you're not near the edges where it fringes. Of course, you saw that in your lab when you did the mapping the electric field. You first map the electric equal potential lines. And then, of course, the electric field has to be perpendicular to equal potentials. So you drew the lines, and you ended up seeing that they were basically a bunch of lines that ran from the positive plate to the negative plate. And only near the top and the bottom did they start to, go out, as opposed to just being perfectly horizontal. So that's where the ED came from. But now's the cool part. What we can do is we can simplify this a little bit by recognizing that there's a D squared in top that's going to cancel out with the D in the bottom. And in fact, what we get is 1/2 epsilon 0 E squared times A times D. Can anybody tell me what this is, this A times D is geometrically with respect to the capacitor? Remember, the parallel plate capacitor had a capacitance of epsilon 0 A over D, where A was the area and D is the separation between the plates. A was the actual area of the plate. So what is A times D? It's the volume between the plates. Okay, and remember, the electric field dies off rather quickly when you get outside outside of the capacitor. So that's where the vast majority of the electric field should be, is really in the volume of it. So this allows us to have a new quantity, which is lowercase u, which is defined to be uppercase U per unit volume. So if you take the uppercase U and divide it by A times D, you end up getting 1/2 epsilon 0 E squared. And in fact, that is the energy density of any electric field. If you want to know how much energy a 1 cubic meter section of an electric field would be, you basically take the electric field strength and square it, multiply it by epsilon 0, assuming you're in air, and then multiply that by 1/2, and that'll be the energy per square or per cubic meter. And if you want to know how much is in that cubic meter, you multiply it by a cubic meter and you get that energy. So that was the result we were shooting for. And part of the reason we do that is later we'll discover there's a device that's not a capacitor. It's called an inductor. And in that case, you end up getting U is defined to be big U over volume, which ends up being big U over the area times the length of the solenoid. That's the shape that I'm talking about. And in that case, you get 1/2 mu 0 times B squared. So that's something we're going to run into later. But again, you see another instance where the electric and magnetic field have very similar results. That's basically a ramification of what Maxwell and the great people that discovered electricity and magnetism and got those 4 Maxwell equations together, is they realized that really there's no such thing necessarily as the electric field or the magnetic field. But in fact, there's just a field of some sort that in one reference frame looks purely like an electric field, and then in another reference frame can look purely like a magnetic field. And that's really what the modern interpretation of it is. There, you can actually do this with relativity and move from a reference frame where there's a positive charge moving through a wire. And from that, because those moving charges create magnetic fields, you can get a magnetic field that, say, circles the wire. But if you switch to a frame in which those positive charges are not moving, then there's no way you can get a magnetic field, because the magnetic field requires the charge to be moving. But lo and behold, because you're in that frame that's moving along with the positive charges, now the charges outnumber the negative charges, and you end up getting basically a electric field that points in the exact same way the magnetic field did and has the exact same magnitude, only now it's called E. So literally you can go from one frame in which you see nothing but a magnetic field, and you can switch to another frame using relativity, and which actually relativity is already consistent with electricity and magnetism, and get exactly the same answer, only now it's interpreted as electric field. Any questions on that? I know that's a lot. Those are big highbrow concepts that a lot of people don't get till they completely finish a 2-semester course in electricity and magnetism. But I'm sort of tipping my hand at you to let you know, because that's sort of what the author's trying to tell you too. You don't have to go through a 1-year course in electricity and magnetism to know that. You should know it just because you took a physics class. All right. Well, those were the last couple things I wanted to make sure I did before I jumped into this. So here's that big paradigm that I was telling you about. So the paradigm is step one, use Gauss's law or Coulomb's law to compute an electric field between two oppositely charged things. Then step two, use the definition of voltage, delta V equals the negative integral E dot dl, to compute the voltage difference between the two charged parts. And then three, use C equals Q over V to find the capacitance. So right here, I have two concentric spherical shells. The smaller inner shell, inner sphere, has a radius of R0. Let me draw that on here so you know what I'm talking about. I'm saying this quantity right here is lowercase r0. And this quantity right here is uppercase r0. Oops. Let me draw that with a different mode on. Okay. So that's the radii we're talking about, is the outside radius of the inner shell and the inside radius of the outer shell. And what we're imagining, in fact, is that the inner shell, the inner shell has positive charge uniformly distributed over it like this, and the total charge amount is plus Q. And then the inner surface of the outer shell has negative charges uniformly distributed throughout like this, and the net charge there is negative Q. So it says there are two concentric spherical shells. The smaller inner sphere has a radius of lowercase r0 and a charge of plus Q on its outer surface. The other has a radius capital R0 and a charge negative Q on its inner surface. A, use Gauss's law to determine the electric field between the spheres. B, calculate the voltage difference between the inner shell and the outer shell. By the way, you don't have to necessarily listen to the directions that I'm telling you in part B. I'm not trying to say you've got to go from one shell to the other. What I want you to do is ideally try to figure out how you could do that line integral such that you get a positive voltage. But if you end up getting it wrong in your guess of how to get that positive voltage, that's okay. Erase the negative sign and use the voltage anyways, okay? And then part C, determine the capacitance of the assembly. So the solution here, which I think I start putting in red, so let's do that. So the solution is going to require Gauss's law, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So I need a Gaussian surface. Need a Gaussian surface that has dA vectors that are all either parallel to the electric field and therefore the E field on that surface is a constant. So they all either need to be parallel to the E or perpendicular to the E field so that the integral E dot dA is equal to 0 for those surfaces. So that's the rule with Gauss's law every time. If you're trying to use Gauss's law to extract the electric field, technically just the electric field magnitude out of that integral, then what you're doing is trying to use your understanding of Coulomb's law and the symmetries that exist with regards to charges to create a Gaussian surface that's closed. It's got to be closed. That's why the circle's on the integral in Gauss's law. And every surface is either parallel, has a dA vector, which you remember the dA vector is perpendicular to the surface and points as if it's going from the outside or from the inside out. So it's either has to have those dA vectors exactly parallel to the electric field, or some of the surfaces could have, for instance, the electric field being perpendicular to those dA vectors, in which case the dot product is going to give you 0, and therefore the integral of the dot product will be 0. And in other words, it doesn't jack up your conclusion. So ultimately, remember, the left-hand side is just going to become an electric field magnitude times some area. It's always going to come up to that. There might be 2 terms or 3 terms or something crazy like that, but all of those terms will either be E times A or 0. Okay. And sometimes you actually you can just call it A, but other times it's really important that you make sure you include the radius or the X coordinate or the Y coordinate or something like that. So I've gotten you sort of started. So we first have to do that for part A. And then for part B, we're going to use delta V, which should be VB minus VA. I'm just using A and B in the alphabet because A comes before B. B looks like it'd be a later result, and that's what delta is supposed to be, final minus initial. But that's equal to the negative integral of E dot DL. Okay. And then part C, we use C equals Q over V to calculate the capacitance. So that's where we're going with this. On the next page, I've already drawn a Gaussian surface. It's a sphere, so you can see it. And I've drawn it at radius R, which you can see by my hypothesis. The electric field, I'm guessing, will have a dependence only on the variable R that we know of from spherical coordinates, or just think about it as the distance from the origin. That's what the R is for any point you're talking about. And it's going to point radially outward, which I call the R hat direction. So that's my hypothesis. And as you can tell, since it's going to point radially outward, the dA vectors on the surface of a sphere also point radially outward. Because it's a closed surface, it has to point as if it's coming from inside the center and going out towards the outside. So it clearly points radially outward, but also radially. Okay. So I can now go ahead and apply the left-hand side of Gauss's law. So this is part A. The left-hand side says the closed integral of E dot dA is equal to the integral. Now I'm going to say E of R hat, dotted. I'll actually make a separate dot and put a parenthesis here, dotted with dA. Now dA, you can technically work it out, but basically like this, the bottom of that little tire patch looking window, that bottom has a length of R times the sine of the polar angle phi from polar coordinates times, yes, excuse me. No, it has a R times the sine of phi times d theta. that's the actual bottom length. And then that side length that you see, the left side or the right side, that's actually going to have a length of r times d phi, the polar angle. But we don't have to do any of that. We're just going to call it dAr hat, and that works just fine. But like I said, if you happen to know those coordinate systems, that's what the answer would be. So now I can see I get the integral of E of R. I'm using the fact that the dot product is a linear operator. So I can take the scalar parts and just put them out in front of the actual vector parts of the dot product. And I get E of R times dA. And then all I have left is the R hat dot R hat. And of course, they're hat vectors, so their magnitude is 1. So it's 1 times the cosine of the angle between them. Well, they're identical vectors, so the angle between them has to be 0, and the cosine of 0 is 1. So the whole thing turns out to be 1. And basically, you're integrating all this over a sphere. Okay, and therefore the surface area of a sphere is 4 pi r squared. So I'm going to get E of R times the integral of dA, which equals E of R times 4 pi r squared. So that's my left-hand side. Does everybody get that? I was explaining all the gory details that go into that left-hand side. You can literally jump from this part to this part, and that'll be just fine. Okay, that's what you're really, you know consistently that the left-hand side of Gauss's law should always turn out to be electric field magnitude times an area. And that's what we got here, so we're feeling pretty good about it. Now, in this case, because of the way the thing is set up, I've got the sphere sitting out of the radius r that's bigger than r0 but smaller than big R0. So I know the right-hand side, which is Q enclosed over epsilon naught, is actually very easy to determine here because, as I said in the previous diagram, the net charge on the outside surface of the inner spherical shell is positive Q. So all I have here is Q over epsilon naught. Now I can set left-hand side equal to the right-hand side of Gauss's law. And that gives me E of R times 4 pi R squared is equal to Q over epsilon naught. And then employing our hypothesis and solving for E of R, I get E is equal to Q over 4 pi epsilon naught R squared R hat. And that is the electric field between the two spheres. Any questions on that? I only got a little bit more time left. So now I'm going to go ahead and do part B. So part B is delta V equals VB minus VA equals the negative integral of E dot DL. Okay. Now, this is a line integral. And remember, we either got to use the DL or we use the range of integration to dictate which direction we're going. I want to go from low voltage to high. I want to go from low, well, evidently I've started to spell low with the letter V. Low V to high V. So delta V is greater than 0. That's ideally what I do. But again, if I make a mistake, it's no big deal. I just erase it, but it gives me good practice. So what I'm going to do is I am going to integrate from, let's say, the point from, let's say, x equals 0, z equals r0, and, or excuse me, y equals r0 and z equals 0, to, in this case, the y is going to be the x is going to be 0 again, but the y is going to be little r0, and the z is going to be 0 again as well. So I'm actually going from outside in. I choose to indicate integration direction with dl. Now, what that means is my dl will point in the correct direction, but my range of integration is just going to be from low coordinate to high coordinate. So now I can say delta v is equal to negative integral. Now it's negative because we're actually using the electric field as if the electric field is doing the work. So that's why that's negative. But the electric field, of course, is Q over 4 pi epsilon naught r squared r hat. And then that's going to be dotted with negative d. Now I am going along the y-axis, but be advised that's the same thing as the radial direction if you're happening to go along the y-axis. So I'm going to call this dr r hat, and the negative shows that we're going in the negative r direction, which is basically the same as the negative y direction. Now I could have changed r to actual y since I was dealing with that, and then I would just say negative dy k hat, or excuse me, negative dy j hat. That would work as well, but I'm trying to stick to the coordinates that we know of or we're used to. So when I do this integral, when I do this integral, I can pull out all this constants. So I've got a negative inside, I got a negative outside. Those two combine to give me a positive. I got a q and a 4 pi epsilon naught. And then all I have is the integral of r to the negative 2 dr r hat dot r hat, which we know is 1, again using the linearity of the dot product. So the integral of r to the negative 2 is 1 over negative 1 times r to the negative 1. So this is going to give me negative q over 4 pi epsilon naught. Remember, the negative came from dividing by negative 1 as a part of the integral. And then, of course, I am going to evaluate it. As I said, I have to go in the positive coordinate direction, which would be from r0 to big R0. So now I'm going to do 1 over r0 minus 1 over little r0. And you notice big R0 is bigger than little r0. So this quantity right now inside the brackets is negative. Okay. And there's a negative sign here too. So we can reverse the order and make it positive, and we'll get Q over 4 pi epsilon naught. And now I'm going to get a common denominator. I've already flipped the order. The order is going to be 1 over r0 lowercase minus 1 over uppercase r0, like that. I'll get a common denominator, and that'll make delta V be Q times R0 minus R0 over 4 pi epsilon naught R0 R0. So finally, we have delta V is equal to Q r0 minus little r0 over 4 pi epsilon naught little r0 big R0. So that is part B. And we got one more step left, and we've got 3 more minutes. So step 3, which is part C. C is just Q over V. So I'm going to say C is equal to Q divided by Q over 4 pi epsilon naught R0 big R0 in the bottom times R0 minus little r0 in the top. You can see that that ultimately gives you C is equal to 4 pi epsilon 0 r0 big R0 over R0 minus little r0, and that's our final answer. Okay, so this process, step 1, Gauss's law or Coulomb's law to calculate the electric field between the positive charged thing and the negatively charged thing. Step 2, use delta V equals negative integral at E dot dl to compute the voltage difference between the positive part or the positive edge and the negative edge. And ideally, you want that to come out positive, and no matter what, you're going to take the positive value, even if you screw up and make it negative by mistake. And then step 3, you're going to take C equals Q over V, and everything that relates to charge should disappear. If you get a capacitance that has a charge density in it, like a lambda or a sigma or a rho or a Q in it, then you've clearly made some mistake. The capacitance should always come out to be a series of geometric quantities like R's and A's and distances and stuff like that. So that's what we got. That's how you do that. I'm going to make some more links that I'll put in this week's module because you need to see some other stuff like disconnecting and reconnecting some capacitors like your book does, as well as putting a dielectric in or pulling the plates apart and determining how much work it takes. All of those things are problems that we need to go over, and you need to understand how to do. So I'm either going to do them next week, or and either way, you should definitely spend the weekend looking at videos of me doing that, just in case I don't get to cover it. So you're free to go. Feel free to stick around. I'll wait for the last person to leave before I leave, just in case anybody has any questions. But thank you for coming, and have a good day.
So I know our test 4 online is due next week.
Right, the
But
15th.
are we still gonna have our second in-person test?
Yeah, I looked at the schedule today. What day do you have lab? You have it on Tuesdays, right?
Yeah, we have it on Tuesdays.
So if you have it on Tuesday, that should mean that your next face-to-face lab should be October 31st.
October 31st. Okay. Let me
You
write
can
it
check
down.
your syllabus to make sure, but that seems to be the right day for me. It has to land on a lab day, and whatever date the week is that I say that you have to have it, that should be the lab day of that week.
And then what chapters is that gonna be on?
Well, we'll definitely have 16 through 24 at least. Because we just finished 23, I think it is.
Yeah.
And yeah, that's 20. No, we're just finishing 24 actually. So we might even have 25 in it by then.
Okay.
Okay.
All right. Thank you. Appreciate it. And then I kept looking for the syllabus. Did you put it in another section aside from the syllabus?
Actually, let me stop sharing and show you where it is. I'll share another screen. Let's go here, and I'm going back to here, and now I'm going to say share screen, and this time I'm actually going to share the computer screen, which will be really, really fancy. All right, so the syllabus is supposed to be in helpful documents and links.
Okay.
Oh, well, wait a second. Evidently, I put it up, but I don't seem to have turned it on. No, actually, no, that's not it either. Where did it disappeared? It's supposed to be one that's dated 9/11. Let me pull that up real quick. I'm going to put it up here. So that might be the problem. Y'all were looking for something that didn't exist.
Yeah.
I swore I did this, but I don't even see it in my files. So I'm going to go ahead and choose it off my computer here. Thanks for asking me about this. I'm glad I did it this way, or I'd be toast not having a syllabus up there. So I can go here. This semester's fall 23. This is my 242 class. And of course, I don't have it in this folder here. It must be in my school folder. Well, that's super helpful. That says 242. That one was last. Nope, that's August. All right. Well, let me track it down and find it for you. It should be put, worst case scenario, it should be up by tomorrow, meaning I have to drive to Virginia Beach and get it. But I apologize for that. That's unacceptable, and I really, really apologize.
It's okay, no problem. Thank you. Thank you for giving me the date, though. That's what I really needed.
You're welcome, and sorry again for dropping the ball on this, but thank you for being so gracious.
Of course. Have a great night.
You too. Thank you.
Bye.
Bye. Anyone else? Looks like that's it. All right, I'm gonna stop share and we'll call it a day. Bye-bye.